Swayam Prabha. Digital India. Educated India.
Hello and welcome to lecture number 28 in the course Advanced Robotics. In the last class, we started our discussion by looking at the grip transform that relates the velocity at the fingertip and the velocity of the object. That is, when you want to move an object with some velocity, that is object manipulation. What is the relation between the object velocity and the fingertip velocities? Then we started our discussion on locomotion, and we said that locomotion basically means moving from one point to another point, either by walking, running, swimming, okay, or in air by flying. So locomotion essentially is moving from one point to another point. And we are focusing our discussion on legged locomotion. That is, we are having legs. It can be a dog which has 4 legs. It can be a human being who has 2 legs, or quadrupeds, hexapeds, who have multiple number of legs to move from one point to another point. We started also talking about gait. And today we will continue our discussion from gait, and then see that when you are having gait, for example, different kinds of gait, and you want to optimize gait, that basically means that we want to go from one point to another point. There could be multiple ways by which we could go. For example, dog has 4 legs, so it can lift the diagonal legs, like in the case of the big dog, and move forward, or it can use one leg at a time to move forward. Okay, so there are different types of gait. We'll start off our discussion from there, and then proceed and see that if you have different kinds of gait, how do you optimize gait? And we'll focus our discussion mainly on biped locomotion, and then we'll see that if you want to build a biped, you want to optimize the energy, how do you do that? Okay, so today we'll continue our discussion on biped locomotion, where we'll see that first we'll talk about gait, and then slowly we'll move towards bipedal locomotion. That is, as the cartoon figure here is indicating, that we are using 2 legs to move forward. Okay, and you can also see that the hands are moving in sync with the legs. And something interesting to note here is that the concept of energy optimal gait, that is, we can walk in different ways, but it's very interesting to note that all human beings walk almost in the same way. That basically means that we biologically, or we have evolved such that our gait is optimal in terms of energy. Okay, so just for historical interest, we said that 1921 Karl Capek was the first person who used the word robot or robota in the Czechoslovakian language when he wrote his play of mechanical men replacing human beings in industries to do dirty jobs. Here also, if you see that the first concept of the robot actually is a biped. Okay, so it has 2 legs, so it's a biped. Okay. Now, Isaac Asimov, 1942, most of his science fiction stories that he wrote also basically considers humanoid robots. So humanoid robots having human capabilities. Okay, like they can do tasks and they can think, they have some amount of AI and things like that. So this concept of humanoid biped is not new as far as science fiction and Karl Capek is considered, but it took us very long to come to biped, essentially because of the fact that wheeled robots were the earliest robots, and wheeled robots were the earliest. Why? Because if you have 4 wheels, you can see that this doesn't require balance. Okay, the robot is balanced already. So if you just leave it there, it stays there. If you rotate the wheel, it goes forward. So control is simple. In terms of energy efficiency, it is simple. Whereas if you talk about a biped, immediately you need what is called balance. That means a bipedal system is essentially unbalanced. It's dynamically unbalanced system. So what we say is dynamically unbalanced system. Okay, and hence we have to balance it always. This would mean that it requires more energy, and it is more computationally expensive in terms of kinematics to get a biped robot to walk. Okay, just revising, here is one of the famous quadruped robots, which is the big dog made by Boston Dynamics. And we talked about gait in the previous class, and we said that gait is the pattern of foot placement. Now if you have a leg like this, And so the pattern of foot placement would basically mean, it does not mean the kinematics or the shape of the leg. It basically means that whether you're making contact with the ground or no contact. So there is contact, or it's in contact or it's in air. So there are two conditions: either it's in contact with the ground or it's in air. Okay, so it's binary, so 1 1 0 kind of. So when the robot is walking, please note very carefully that the leg contacts, there are four legs here, so there are four contacts. And if I draw the top view of the robot like this, okay, there is one leg here, one leg here, one here, and one here. Okay, then you note very carefully that it is having diagonal kind of gait, which basically means that these two legs will be in air, then it will switch and the other legs will be in air. So first the red color will be in air, then the yellow color will be in air, and that is the way it is walking. So at any time, two are in air, two legs in air. Okay, that is the way it is, a diagonal kind of gait which this robot is using to move forward. Okay, the other thing that you should note is that if you look at the shape of the legs, please look very carefully. If I draw the side view, the shape of the legs is inward bent like this. Okay, whereas in the case of a dog, it could be forward bent like this. Okay, so this is basically, it is probably more stable gait that it is having. So please note these things in the video very carefully, and then today we'll discuss in more detail what do you mean by the gait, and how do you optimize gait, how do you do the kinematics, etc. So please note the gait that this robot is using. At any instant, two legs are in air and two legs are in ground. So in between, the robot could instantaneously be on four legs on the ground also. Okay, but that is a very small, very, very short phase. Okay. So this is basically showing that the robot is walking in such a way that two legs are on air on any instant. Look at the shape of the legs, they are bent backwards. Okay. So today we'll also look at, we'll also have a discussion on degrees of freedom of the legs and things like that. Now this is a bipedal robot, which is Atlas, also made by Boston Dynamics, and it can walk, it is bipedal. Okay, so again, if this is my head and this is my hands, the hands are not doing much. You can see they're just standing there, they're not moving. And if this is the side view, then the robot is like this. Okay, please note that the legs are bent there, they're not straight, they are bent. So today we'll also try to see why the legs are bent. So if you see a bipedal robot walking, you'll always find that the legs are bent, it doesn't walk straight. Human beings walk straight. Okay, so if I talk about a human being, now this is a human, our legs would be like this, straight. Okay, there is no bend there. Whereas in the case of the robot, it is like this. Okay, that is essentially because for balance and stability, this kind of bent structure is more stable than this structure, because this behaves like an inverted pendulum otherwise. So it can fall very easily in that side or this side. Okay, so this basically showed a bipedal robot which is walking and going from some point to some other point on the ground, and it is also having a gait. Whereas in this case, there are two legs, so the gait would have one leg on air, then two legs on the ground, one leg in air, and then two legs on the ground. So it's 2 1 2 1 2 1, which is a little different from the gait of the big dog that you just saw some time back. Okay, so we'll discuss these things in more detail today. Okay, so we said that the gait is the pattern of foot placement. So this basically means whether the leg is in air or on ground. Okay, so there are two conditions only. Now if it is on ground, we mark it with a black color, and if it's in air, we just leave it blank. Okay, so to talk about gait of a biped, so for a human being, if I take my front view here, okay, these are two hands on the two sides, these are legs, two legs. And if I take the side view will be something like that. This is my side view. Okay, and these are the arms. So we have two legs. So we can talk about this as the right leg and this the left leg. So if I draw my gait diagram, this is going to be right leg. Okay, this is my right leg and that's my left leg, and it is this is a different instance of walk. Okay, so this is T1, T2, T3, T4, like that. Okay, so this is my left leg, that's my right leg. Okay, now when we start off, normally we are on two leg stance, so both legs are on the ground, means it is like this. Then one leg goes up. So if I take the side view, one leg is in air. If you can imagine, this is my rear leg which is in air, and this leg will go like this, and this fellow is on ground. Okay, so the rear leg will go forward like this and become the front leg, and the body moves forward. Okay, so we are in two leg stance, which is this one. Then we come on one leg stance. So the right leg is on the ground and left leg is in air. So the one that is on the ground is marked with a black dot. The one that is in air is left blank. After this, the next instant will be two legs on ground. Then it is going to become one leg on ground, then two legs on ground. Okay, so this is the gait for a biped. So you can see that it's one leg. So it is one leg, two legs, one leg, two leg, like that. Okay, on the ground. That is the way we walk. Now, what is the difference between run and walk? Interesting question. So in walk, normally, rather, it will be this cycle. This is walk. So one leg, two leg, one leg, two leg. That is walk. What is run? Run can mean two legs on air, two legs in air. Okay, and then one leg on ground. Okay, so the running gait would have instances where both the legs are in air, whereas walking is basically an instant where either two or one leg will always be in contact with the ground. Okay, that is the difference between running and walking. Now let's see further. In the case of a quadruped robot, which has four legs, so this is the forward direction. This is the forward direction in which the robot is, let's say this is a dog. Well, this doesn't look like a dog, maybe it's a robot. Is walking forward. Okay, so this is it has four legs. So this is my right front, this is the right back, this is left front and left back. So there are four legs and each of them are marked here. Okay, now you can see that in instant T1, this is my instant T1, there are two legs on the ground. This one is on the ground, that is on the ground. So LB and RF are on the ground. So we are marking it with a black color here and here. Okay, at this instant T1. At the next instant, what is happening is here, T2, which is also called the changeover phase. Okay, so it is basically changing the legs which are in air. What is changeover? Changeover phase is the phase where legs in air interchange. Okay, so in the case of the biped robot, if the right leg was in air, then it will become two leg and then the left leg will go in air. Okay, then again the right leg will go in air. So this change phase is called the changeover phase. Now in T2, all four legs are on the ground. They are marked with black dots. So you can see that all four are on the ground. T3 is in the first case the right was on the ground. So now the left is on the ground. Okay, so the left is on the ground. Okay, and then all are on the ground again changeover phase. So this is the way it goes. This is basically called the gait diagram. Now, because there are four legs here now, is there any other way by which this can move forward? Yes, of course. Say for example, if you have four legs like this, okay, if I'm drawing it this way, then at any one instant you can have three legs on ground, and one in air. Then four can be on ground, then one in air again. Okay, so rather, let's say four legs on ground, one in air, then four on ground and one in air again. So in this case it is 2-2. There's two legs which are in air. I'm saying that you can also walk, this robot can also walk with one leg in air and three on the ground. Okay, because it has that option. In the case of biped, we don't have an option. You have two legs only. So either both the legs are on the ground or one is in air. Both can't be in air, because if both are in air, then it's running, it's not walking. So here basically we are saying that there is a different way for having a gait. Now if you're saying one leg is in air and three are on the ground, okay, but then which leg is in air? So depending on your gait, you can actually have a different leg in air each time. So you can have different types of gait. Okay, that is what we are going to see today as we go along. Okay, so we talked about static balance and dynamic balance. So in static balance, we are basically saying that the robot is walking very slowly. It's almost like it is static. Okay, so accelerations x double dot is almost good as zero. Okay, accelerations are very, very small or they're almost zero. So in that case, how do we define balance? We define it by saying that in this case, we have a hexaped. We have 6 legs. And at this instant, 3 legs are in air. And 3 legs are on the ground. So this, and this are on ground. Now the legs that are on ground, if you join them with straight lines, what you get is a support polygon. This is called the support polygon. Now in the support polygon, the projection of the center of mass if the projection of the center of mass lies inside the support polygon, we say it is balanced at that instant. Okay, and how do we define it? We can come here and see. So this is the top view. If you see it from here, what you'll see is this triangle. This is the top view, and this is the projection of center of mass. The distance d1, d2, d3 from either of the boundaries is called the stability margin. So the minimum of this distance d1, d2, d3 is how stable it is. For example, if the center of mass were to go this side and d2 becomes this small position, then it is less stable. Okay, so that is one definition of stability margin. The other is longitudinal stability margin. In the direction in which the robot is moving, you have d1 here and d2 here, the distance from the boundaries. Okay, so the minimum of d1 and d2 will give you the longitudinal stability margin again. Okay, but please note this is static balance, so it is walking very slowly. And now let's look at different kinds of gait. So this is a quadruped. So this is a quadruped robot, means it has 4 legs. Okay, we are not talking about the shape of the legs, we are not talking about the size of the legs. Those things we are not considering. Here we are just considering the gait, the pattern of foot placement. Now in this case, in this quadruped, we are saying that at any instant, at a time, or rather let's say at time t, okay, either 4 legs are on the ground or 1 leg is in air. Okay, 4 on ground or 1 in air. 1 in air means 3 on ground. Okay, that's how it moves forward. Okay, so basically it has 4 legs, 1, 2, 3, 4, which are marked in this figure here. So if you look at the gait diagram, then what we are seeing is that at any instant we have the number of legs which are on the ground can vary now. Okay, 1, 2, 3, 4 of them are there. So let's see here. This is called the wave gait. This gait is called the wave gait. So 1, 2, 3, 4 are the leg numbers. So 1, 2, 3, and 4. So at time equal to 0, okay. So in this case, they are using normalized time, which means that one full cycle is made up when 4 legs have moved. Okay, that means I'll just explain what that means. So it basically means that at 0, 1 leg is in air, 3 legs are on ground. Okay, then the next instant all legs are on the ground, then 1 is in air again. Okay, so here the next instant would be 1 will be in air. So here 3 are on ground. Here this one is in air. Okay, here this fellow was in air. Next this fellow is in air. Then this fellow is in air, and then that fellow is in air. Okay, and in between all are on the ground here. So at this instant you see they are all on the ground. Okay, so let me explain it again how they are drawing this gait. So here you are seeing this one is in air, then all 4 are on the ground. Then this one is in air, all 4 are on the ground. Then this one is in the air, all 4 are on the ground, and then this one is in air. So all the legs have been in air once. So this fellow 4 was in air, then 2 is in air, then 3 is in air, then 1 is in air. Okay, and in the changeover phases, so this is my changeover phase. Okay, in the changeover phase, all 4 are on the ground. Okay, now this means that at any one instant, 1 leg is in either all 4 are on the ground or 1 is in air. Okay, now if that be the case, then what is the way by which leg is going to be in air? Okay, so if I look at this figure now, this figure basically tells me the cycle in which it is going. The first leg is in air, then number 2 is in air, then number 4 is in air, then number 3 is in air, and then number 1, it comes back to 1 again. Okay, so whereas you can also have this cycle in which it starts with 1, then becomes 4, then becomes 2, 3, 1. Okay, you can have the other way around also, 1, 2, 3, 4, 1. Okay, so these are all the various possibilities of which leg is going to be in air, or what is the sequence in which the legs are going to be in air. So each of this will have one diagram like this. Okay, I hope you understand. Here basically what we are saying is that there are 4 legs. So which one is going to go in air? For example, let me take the example of the first one here, the first diagram here, and say, so the first one is in air, this one is in air, then the second one is in air, then the fourth one is in air. So like this, fourth one is in air, then third one is in air, and then comes back like that. That is this one. Okay, or we could have cycled it such that if I take this one now, let me take this one. if I cycle it that way, let me change the color. So if I take this example now, so it is 1 is in air, sorry, it starts from, 1 is in air, then from 1 what will happen, the fourth is in air, this is in air like this, okay, then from 4 it is 3 is in air like this, and then from 3 it is 2 is in air, then it's 1. So you can see it's a cross kind of a gate which is coming, that is this one. Okay, so these are all the possibilities by which this four-legged robot can go forward, and this gate is called a creep gate. Okay, it's also sometimes called a wave gate of a quadruped robot. Now there are two terms which are called, which is called duty factor and phase for time. Okay, what is duty factor? Duty factor is which is defined by beta, so support period of leg I by total time t. Okay, so total time t would mean the total time for which all the four legs have actually moved. So here it is like, that is where this 4 is coming from. So it's like there are 4 phases here for each of the legs to move once. Okay, so the duty factor beta is equal to 0.75 in this particular case. Okay, now this gate is called the creep gate. Now you can have more number of legs, like this is a hexaped. Okay, so this is a hexaped having 6 legs. Now in this 6-legged robot, we are having a wave gate, okay, which is having a beta of 2 by 3. Now in this case, at this instant, you see that there are 2 legs in air. This is in air and that is in air. Okay, so 5 and 4 are in air. So 5 and 4 are in air. Okay, then what is happening is at this instant, this 5 is in air till now. Okay, and these 2 are on ground. Then what we are having is this fellow is in air. Okay, and this are on the ground. Okay, so this is a kind of gate which is also called wave gate with the beta equal to 2 by 3. Okay, so wherever this line is there, that means at that instant it is on the ground. So this is on the ground. Okay, so this one, number 5, is on air. Okay, now in this particular case, it is 2 is in air. Okay, and then here 3 is in air, and here 6 is in air. So at any one instant, one leg is in air here, you can see. Okay, so at this instant, you can see 1 is in air, here 1 is in air, here 1 is in air, here again 1 is in air, right? So this again can have different combinations, which leg is going to be in air, because there are 6 now. In the previous case, you had 4. So you had this many variations which are possible. Now you have 6. So there are more number of variations which are possible. Okay, now wave gate with duty factor half is this one. Duty factor half basically means, half here means how many of them are in air. Okay, so if it is half, that will mean half the legs are in air. So it is 3 is in air, 2 is in air, 6 is in air. Okay, this is the meaning of half. Okay, so please go back to the definition of support period of leg I by time t. That is the meaning of the duty factor. Okay, so here we are getting this fellow is fully in air here. That means half the time this fellow is in air, then other half of the time this fellow is in air. Okay, and there are 6 legs, so there are 6 parts. So this is 1, 2, 3, 4, 5, and 6. Okay, here duty factor 2 by 3 means the same thing here. Okay, which basically means that out of total time, if I do 2 by 3 into 6, okay, there are 6 parts. So into 2 into 2 is 4. Okay, that means 4 legs are on the ground at any instant. So there is 1, 2, 3, 4 on the ground. Okay. Okay. So this is basically what we talk by wave gate and creep gate. Now you can also have pace gate and bound gate. This is something that we have seen in the case of the quadruped robot, like the one we were just looking at the video in terms of the big dog. Okay, in that case, it was using diagonal legs for moving. So 2 legs were in air at any instant. Okay, so in this particular case, in this pace gate, this is my pace gate. So 1, 2, 3, 4 are the leg numbers. 1, 2, 3, 4. So 1, 3, 2, 4 are here. You can see that this instant, okay, 2, 4 are in air. Okay, 1, 3 are on the ground. So 1 and 3 are on the ground, and the other 2 are on the air. Then there is a changeover phase, and then what happens is the other 1 and 3 come on the air, 1 and 3, and then 2 and 4 are on the ground. That means it is going not diagonally but sideways, these two legs, and then these two legs are interchangeably in air. Okay, so it is not diagonal, it is side. So if I draw the legs like this, then what it basically means is these are my four legs. Okay, then it is going this side and then it is going this side. Okay, and interchanging. In the case of the big dog, it was crosswise. It was like this, like this, like this. So in the case of the big dog, it was like this, and then it was like this. Okay, so this is what we call by a pace gate, and the gate diagram is shown here. Okay, so the other gate is the bound gate. Okay, so this is my bound gate, which can be used for running or jumping also. So this is a bound gate in which we have 1, 2, 3, 4 legs. So we have 3 and we have 4, which is in air. So 3 and 4, that means the front sides, in that particular case, if these are the 4 legs, then the front is in air. Okay, it is like this. These two are in air. Then in the next shot, 4 are on the ground, and then this is in air. Okay, so this was the big dog. Okay, this is basically what we call the pace gate, where it is going sideways. Sideways legs are on air or on ground, and here this one is called the bound gate. Okay, in the bound gate, only the front legs or the back legs are in air, and this is my gate diagram. Okay, now these are different kinds of bipedal robots that have been built for a very long time. Quadruped robot inspired by mammals. Big dog is probably the best, and these are the corresponding gate diagrams for the robots. So please draw the gate for the big dog. If you draw the gate for the big dog, it will turn out something like this. It is diagonal legs which are moving. Okay, so it will be almost similar to this. I talked about the instantaneous support. Okay, so this can be instantaneous. That means the 4 legs on the ground for the big dog, one leg would be instantaneously on the ground and it will take off. Okay, now yeah, so this is the concept of gate. Now let's move forward and look at frames at joints. Now we have seen that we define each leg. So this is my leg. Okay, this is my leg. Okay, and there is contact here. This is my this is the leg. Now the first question that comes out is how many degrees of freedom. Now if we say it is 2 degrees of freedom, then the 2 degrees of freedom will be one joint here, one revolute joint here, one revolute joint here. So it's a 2 DOF, the simplest. Okay, you cannot have one DOF, so it will have 2 DOF for each leg. Now if this is the body here. Okay, so that's my body, and there is another sorry, the legs must be of, what will be the length ratio of the lengths? They'll be same length. Okay, this is something which we said. Okay, so this is my 2 legs, and these are degrees of freedom which are there. So each leg has degrees of freedom per leg. So each leg has 2 degrees of freedom. Okay, so each leg has 2 DOF. Okay, now we are going to do the kinematics of this. So basically I need to put frames at the joints. So we have to follow the DH parameters to put the frames at the joints, and then we can have a global frame. So what I need to do is put frames at the joints, and this will be my z-axis, okay, as per DH notation, and then correspondingly I can put the x-axis. So x-axis can be this side. Okay, so the first thing that we need to do is to put frames at the joints, and we can relate the frames by means of the one is the rotation matrix. Okay, that is one, and the second is the homogeneous transformation matrix. Okay, so the rotation matrix is something which we have studied. So rotation is always about z theta, and that matrix is cos minus sine cos 0, 0, 1. This is something we did at the beginning of the course. And the homogeneous transformation matrix basically relates two matrices n minus 1 to n, and this consists of the rotation matrix here and the translation between the two origins. This is 0, 0, 0, that is 1. This is the distance between two frames. Distance between origins of two frames. Okay, that's the homogeneous transformation matrix. So by using the homogeneous transformation matrix, we can actually find the relation between one frame and the other frame. And in order to find contact, I can put another Z here and put an X here. Okay, because I want the contact point also. So although there's 2 degrees of freedom, I basically want the relationship of the end of the foot also with respect to the body frame. Okay. Now this is exactly how we do the frame assignment. Now please note that unlike a serial arm manipulator, this robot is moving around in space. Okay, so we need to put a local frame and we need to put a global frame. Now this is my global frame or fixed frame, okay, which is fixed and which doesn't move. Then I put a local frame okay, which is put at the center of the body. Sometimes it is put at the CG of the body. Okay, so global frame and local frame have been put. Local frame is at the CG of the body and global frame is put anywhere outside. And I know that this one to start off with. What is that vector? I know that vector. Okay, that means I know what is the local frame with respect to the global frame. Yeah. Now, how does it move forward? Next is I have to put frames on each of the, or I have to put frames or axis at each of the joints. So let us assume that the degrees of freedom per leg is 2. Okay, so it has 2 DOF per leg. Okay, so there is 1 DOF here and there is 1 DOF here. And I also need the foot point contact. So I have my Z axis in this direction. So these are my Z axis. Okay, and by using the homogeneous transformation matrix, I can go from here to here, here to here, and then from here to the local frame. Okay, that means I can find what is the contact point. I can find transformation between foot contact, foot ground contact, and transformation between foot ground contact and the CG frame. And if you have with relation to the CG frame, you can also go to the global frame, right? So, and this can be done for each leg. For each leg, so you can look upon this as a serial arm manipulator. Okay, you can, if I reverse the problem, suppose you are thinking, suppose I invert the problem. What do? I put this robot upside down. Okay, so if I put it upside down, what will happen? This leg is like this now. Okay, so the body has come down and this is my CG now. Now this is like a serial manipulator. It's exactly same as a serial manipulator. You would have studied the robotics of the frame assignments of serial manipulators in most textbooks. So here what we are seeing is that if I consider this to be a serial manipulator, this is not moving. This is my Z axis, X axis, Y axis. Then this is 1 degree of freedom, this is another degree of freedom, and this is the contact point XY. We can say XYZ also. Okay, so each of this is behaving like a serial manipulator. Okay. And then now you know how to do the frame assignments and do the kinematics. Okay, so it is exactly similar to our serial arm manipulators, where we are considering each arm to be equal to a manipulator. Okay, so each arm is equal to a manipulator. That is how we are modeling this and how we do the kinematics. Okay, now the robot has to move forward. How does it move forward? So this is a quadruped. There are 4 legs. So at the simplest case, we can talk about a creep gait or a wave gait, such that at any instant, one leg moves forward. Okay, so this is the leg which is moving forward, this leg here, and it takes a trajectory like this and comes here. For example, I can say the leg was here. Okay, then it is going to go like this and it will come there. Okay, so I hope you can imagine. So the leg, the tip of the leg is having a trajectory which is like this. That's how it's going forward. And when that is happening, the body is also moving forward by some distance. So the body will also move forward by some distance. That means what is happening is that the angles of this leg are changing. Of course, this is a 2-link manipulator. There's 1 degree of freedom here, another degree of freedom here. So it is behaving like a two-link manipulator like this. So it is taking a trajectory like that. Okay, this is a fixed point. Now this point is also moving, and in the other legs, because the body is going forward, this leg will bend slightly forward like this. The body has gone forward now. Okay, so which basically means the body has gone forward now. I hope you can imagine that. Okay, so these points will be on the ground, but the joint angles will change a little bit such that the body goes forward a little bit. So the body will come here now. Okay, and in the process, this one leg has gone here. The next, so that is one step. In the next step, all four are on the ground as per the gate diagram. Then one leg is going to go on air again, one of them. So it could be anyone depending on which gate you're following. Okay, so suppose the next one is this one goes in air like this. Okay, so this one is going like this. In that case, it will go like this. Okay, and the body goes forward a little bit more. So what you're seeing is that as one leg is going forward, the body is going slowly forward. Okay, so you have to do the inverse kinematics of this two-link manipulator system. And inverse kinematics of two-link manipulator system is very easy, which we have studied before. So after we do the frame assignments at joints as per DS notation, we have done inverse kinematics of the arm. So inverse kinematics of 2DOF systems we have done. Okay, so please look at the earlier notes. So it is something like this. So for a fixed link manipulator, it is like this. Okay, now this is like the leg, the inverted leg. Okay, so there is one angle here, θ1, and this is my θ2. Okay, this is my point xy. This is L1, this is L2. So I can find the values of, so x is equal to L1 cos θ1 plus L2 cos θ1 plus θ2, and y is equal to L1 sin 1 plus L2 sin 1 2. And I can solve this. θ2 is equal to, this is x squared plus y squared minus L1 squared minus L2 squared by twice L1 L2. This is cos θ2. Then I can find sin θ2 by taking 1 minus cos θ2 squared, and then I can use the a tan 2 function. So θ2 is equal to a tan 2 sin 2 cos 2. Then I can find θ1. Okay, so this has been done. So basically we can, given a trajectory here, what kind of trajectory we are following? Some trajectory like this, right? So trajectory was like this. I've drawn it upside down so that you can understand. Now it can be the other way around also. The way it was in the robot was like this. The leg was like this. Okay, so here we are having my angle θ1, and this is my angle θ2. Okay, so this is having a trajectory like this. Okay, okay, so basically this is what the trajectory was here, this trajectory. So this is my angles θ1 and θ2, and this is the trajectory of the end effector. Okay, now this is also moving. So this moves little bit determined, that is determined by how much the body is moving forward. So we can do the inverse kinematics this way and find what are the joint angles when the robot is moving forward. Okay, so inverse kinematics means I give you these points. Okay, it can be a cubic spline. We have studied cubic splines, so it can be a cubic spline that the leg is following a cubic spline. So you can find the xy coordinates. Then for every xy you can find what is θ1, θ2, and then this also moves forward a little bit. Okay, so this is how we do the inverse kinematics of the quadruped robot. Each of the legs is considered to be a single manipulator which is moving. Okay, and we are going straight, so 2 degrees of freedom per leg is okay. This robot cannot turn, it can only walk straight. So this fellow can only walk straight. Okay, for straight walking this is enough. If you want it to turn, then you have to increase the degrees of freedom. Okay, so if I want the robot to turn also, then I'm going to need 3 degrees of freedom. Okay, so let me just go back here. So straight walk, we have the robot which has 2 degrees of freedom each, so 2 df per leg. Now if you want to turn, then you need 1 more degree of freedom, which is about this axis. Okay, so this is one axis, second axis, so you'll need one which will be about that axis also. Okay, so it needs to turn. Okay, so for turning you need 3 degrees of freedom per leg. So for turning you need 3 DOF per leg. Okay, So if it's 3 DOF per leg, then it is 3 into 4, which is 12 degrees of freedom system, and this is 2 into 4, which is 8 DOF system. Okay, this is for quadrupeds. Now this is how you do the inverse kinematics of this robot. Now how much it will go forward, that you can determine. Okay, so per leg is going this much, so the body will probably go half of that. Okay, or maybe 1/4 of that. That you need to fix geometrically, as you need to move this also as it is moving. Okay, this is an example of a gait of this quadruped robot. Okay, so at any one instant you see it is taking one leg only. Okay, so these are very simple robots which are made by students. This has 2 degrees of freedom per leg. At any one instant, it is simply moving one leg forward. 3 legs are on the ground, then 4 legs are on the ground, then 1 leg is in air, that way. Okay, so this is what we call creep gait or wave gait. Okay, now you can have different variations of it. For example, you can have diagonal gait, as in the case of a big dog. Okay, but it's more difficult to control. So now you would understand what we are talking about in terms of stability. So when we talked about stability, so we talked in terms of stability and said that if this is the robot, when we talked of static stability, okay, so these are 4 legs, and we said that if 1 leg is in air and 3 legs are on the ground, if I assume that these 3 are in air, then the triangle made there is called the foot support polygon, and the projection of the center of gravity has to lie in that foot support polygon. That is what we saw in terms of static stability. Okay, so this is my foot support polygon, and if I see the top view of that, so the top view will be something like this. Now let me draw the robot in this configuration. So these are the legs, and at any instant, let me say that 3 legs are on the ground. So this and this are on the ground. So my polygon is like this now. If this is the CG, projection of center of mass is in the polygon now. It is balanced. The moment I say I'm using a diagonal legs to be in air, so if this is my diagonal legs, those 2 are on air, what is happening to the foot support polygon? It is becoming a line. Okay, so the center of projection of the center of mass has to lie on that line. Okay, otherwise it will fall. Okay, so in terms of stability, this diagonal gait is not very stable. A creep gait is much more stable because you have a bigger polygon. Okay, but using this diagonal gait you can walk faster because 2 legs are in air. Okay, and this is a dynamic kind of a balance which is going on. As we come to dynamics, we'll see what do you mean by this dynamic balance. Okay, so this gave us the example of how the robot is walking forward. You can do the simulation of this very easily, considering each leg to be 2 degree of freedom manipulator arm, and at any one instant only 1 leg goes forward, 3 legs are on the ground. Okay, now as we proceed, we looked at quadrupeds, we looked at gait. Slowly let us move towards the area of bipeds. Okay, so when we're looking at bipeds, as the name indicates, have 2 legs. So biped, as the name indicates, means 2 legs. Okay, and now these 2 legs, interestingly, these 2-legged robots or bipeds, they can be active or they can be passive. Okay, what is an active biped and what is a passive biped? Now, for this system to move, you have to give it energy. For any system to move, say if I have a mass which is lying here, I want this mass to move, I have to give some force, which basically means I have to give some energy to the system to move. Okay, so I have to give some push to the mass, then the mass will move and come there. So I have to give some force into distance, F into d. Some energy has to be given to this system to move, right? So for this biped also, it requires energy to move. Okay, now in the case of an active biped, it has motors at the joints. Okay, so you can see that this is an active biped. The one on the left hand side is an active biped, and these are motors. So these are servo motors. We had discussed servo motors. So each of those joints have servo motors. How many degrees of freedom? Let's not worry about it now. Let us just say that it has 448 degrees of freedom. Okay, so there is 2 degrees of freedom here, 1 here, 1 here. Okay, so there is 4 plus 4, 8 divided, and it has 8 degrees of freedom, and it can walk straight. Okay, now each of these motors, you are going to give voltage to the motors, and the motor will rotate. That is where the energy is coming from. So energy means electrical energy. Okay, so this is basically called an active pipette, which has active motors which are being controlled such that the robot can move in a particular direction. Okay, now can you have a robot or a biped robot which doesn't have motors but can walk? The immediate question comes, where is the energy coming from? Okay, now this is an example of a passive biped. Now a passive biped has no motors. Okay, and you can see here that this passive biped, there are no motors here. There are links and there's a revolute joint there, and these are legs which have a particular shape. Now where is the energy coming from? The energy is coming from gravitational energy. Energy is gravitational. It's basically gravity or gravitational energy. Okay, so this can walk on an inclined ground. It cannot walk on flat ground. Okay, and the concept is very interesting. The concept is like that of a wheel. Okay, so this is the wheel. Let me draw a bigger picture here. So this is a wheel. This is a much bigger picture I'm drawing. When the wheel is on flat ground, what is happening to mg? This is my point of contact. This is mg. This is the point of contact. Okay, so there is a force. So this mg force is coming through the point of contact, and there is no moment there. So the wheel, when you're keeping this wheel or a ball on a flat ground, it will not rotate. Why will it not rotate? Because there is no moment to make it rotate. Now the moment I keep the wheel on an inclined surface, like if I keep it like this, now what is happening? This is my contact point, and the mg is like this now. Okay, mg is coming here now. Now this is the contact point, and mg force is coming this way. Okay, so what is happening is this force into that distance is a moment which is being generated about that point. Okay, so what is happening? Because this moment is generated about this point, this wheel will start rotating in this direction. That is why it rotates. So if you keep a wheel or a ball on an inclined surface, it will start rolling down. Why is it rolling down? Okay, so why is it rolling down? It is rolling down because of this. So exactly same here, what we are seeing is on an inclined plane, if I keep, this is my contact point, mg is going like this. So there is this mg into that distance x. So mg into x. Okay, mg into the distance x is the moment that is coming, or the tau which is coming about this point, and this is going to make the wheel rotate. So now you would have seen bicycles. Okay, I'm sure you have seen bicycles. Now these bicycles have spokes on the wheel. Okay, so this is a wheel. Let's say this is a bicycle, and this is spokes which are there on the wheel. Now if I just take this one and this one, let me change the color. So if I take a part of a wheel, only this much, okay, then there's one spoke here, another spoke here. Okay, and this is behaving like a part of a wheel. Now if this is behaving like a part of a wheel, then this should apply. That means if I put this on an inclined ground, this is my ground like this now. Okay, it's making contact here. What will happen? This will rotate because mg is going this way now. Okay, so this is a part of a wheel, and this is the way it is shown here. So this is one leg, this is another leg. So this is one leg, this is one leg, this is another leg, and this is one leg like this. It's a part of a wheel. Okay, so very clearly you can see that this is like, it's a complete wheel. This one is like a wheel. Okay, like a bicycle wheel which has spokes. And what you have done, you are just taking this one and you're taking this one. Okay, so what is happening is that it's becoming like a part of a wheel, and this is the part of a wheel. This is one leg and this is another leg, and this fellow's sole is like this fellow's sole is like this. Now if I keep it on an inclined ground, it will start going back, it will start going down. Now it can rotate about, this is a revolute joint. So what is going to happen is, if I keep it on an inclined ground, this leg will go forward, body will go forward, and will keep moving forward like that. Who is giving the energy? Okay, so this wheel is rotating here. Where is the energy coming from? It is coming from mg, which is gravitational energy, right? So gravity is pulling it down. That's why it's rotating. Okay, so this kind of robots are basically called passive robots. Okay, they can be called passive robots. They are also called self-propelling systems, self-propelling machines. Self-propelling means that there is no energy that is being given. It is walking by itself. Okay, now if you're not convinced, you can have a look at this one. This is the video which is showing a self-propelling machine or a passive walker which is walking down a slope. There is no motor anywhere. So there are two legs which are connected by a revolute joint, and if you look at the shape of the legs, they are circular or spherical actually. Okay, so they are bending from side to side and it is walking forward. There is no motor anywhere, so it is behaving like a wheel and it is coming down and coming down for and walking, right? So this is basically what we call a passive walker, and these are called passive robots. Okay, they walk by themselves. Okay, this is an interesting you can make one yourself, where you can make a passive robot and make it walk by itself. Okay, now this is another example. This toy is a passive walker and it's called tuk tuk. Okay, because it makes the noise tuk tuk when it is walking. And how does it walk? These are two legs. This is one leg, there is another leg. Okay, two legs, and the shape of the legs, if I draw it here, if you see, the shape of the leg is like this. Okay, so it is semicircular here and semicircular legs are there. Why semicircular? So that it can bend on this side and it can bend on this side. Okay, and it walks forward. So the shape of the leg, if you look at the previous one, if you look at the passive walker that we have shown here, if you look at the shape of the leg, it's semicircular here. Notice very carefully. On this direction, also in that direction. Okay, so this is my leg. It's like part of a sphere. Okay, that is the shape. So it can bend on that side and it also rotates on this side. So if you look at this passive walker that was walking, you'll notice that it is actually bending on side to side and also rotating or rolling in the front direction. Okay, so like the legs are a part of a sphere. Okay, now this is tuk tuk, which is the toy, and it has weights on both sides. Okay, so it is walking down an inclined surface by bending side to side. So it will go from this side to this side, so that the contact goes from this leg to this leg. So the contacts are basically changing. So if I draw it here, one leg is like this. Okay, the other leg is like this. Okay, and there are weights which it is carrying from this side to this side. So once is that side, then is this side. So contacts are changing from this leg to this leg. So one leg, it is changing from left, right, left, right, left, right. And because it is inclined on the side direction, if I draw the side view of this, the leg is like this. Okay, so what is happening? This is part of a wheel. So it is rolling down. Okay, so let's have a look at the video. It makes it very clear how it's working. So you can see that this is no motors anywhere. So no energy being given to it. How is it walking down an incline? It is getting the energy from the gravitational energy. Okay, so gravity is pulling it down, and that is how the energy is coming. And this is a very interesting walker, which is called a passive walker. So there are several types of these passive walkers which are used to study dynamics, in order to understand dynamics of passive systems like this. And these are the simplest biped robots which can walk with no motors. Okay. Yeah, so those are passive walkers, but now let's look at dynamic walkers. Now dynamic walkers require balance. Okay, why? Because as you see that the biped robot is walking, so there is some acceleration which is there. Okay, so acceleration, correlative centrifugal forces and gravity forces are there. Now a bipedal system is inherently an unbalanced system. Okay, so this is an unbalanced. Okay, what does it mean? So if you look at this, this is basically having 1 degree of freedom here, like this, and there is a rotating degree of freedom there. Okay, so by controlling this degree of freedom, it can basically jump up and down because there's a spring there. Okay, so it can change its position of the body like this. Okay, and if it changes the position of the body, what would happen is the CG is being shifted, right? So it can go this side or it can go this side now. Okay, so depending on that, and it can jump up and down by moving the springs there. So this is the one of the earliest biped robots, which is basically a jumping robot, and this one can jump up and down, and it can go forward. Okay, now this gives us an idea of dynamic balance, and this is a robot which is controlled. So this has 2 controls are there. Number 1, the first control is controlling the body altitude. That means this inclination angle I'm going to control. Okay, so this I can control by controlling the position and the velocity this way by using a PD controller. So this is a PD controller which is controlling the altitude of the body. The second is the amount of extension that is there is L. Okay, so this I can control by also looking at FL is the force that is by controlling the hopping height. So I can control the hopping height by using FL is equal to this equation, which is also PD controller. So that's P, this is my P part, and this is my D part. So by using this, controlling both of this, I can actually control how this is hopping along. This is basically called an hopping robot. Okay, the video is not working, but in the next class we'll start off with this video. So this basically shows us the simplest hopping robot, which is dynamically unbalanced, and because of this dynamic unbalance. Okay, so today we looked at the concepts of gait, then we looked at active biped, we had looked at passive bipeds, and we saw the different kinds of passive bipeds, and then we slowly moved towards active bipeds, that is this hopping robot. So in the next class we'll start off with the video of the hopping robot, which makes it very clear how the robot can hop around. Okay, so you can control it's basically jumping, and it's statically unstable. Why? Because it cannot stand in one place. If you try to make it stand, it will fall. Okay, as long as it is jumping, it's okay. But the moment you want it to stand, it won't stand because it is dynamically unbalanced system. Okay, so these were some of the earliest robots which were called hopping robots, and in the next class we'll continue from here. We'll look at the video of this hopping robot and see how we proceed towards design and control and optimization of bipedal systems. Thank you. So we'll stop here today. Thank you.